AP Review Packet 3, Day 3. Today we're going to be talking about bivariant data, FUDs, and residuals. So if you could turn to your Packet 3 that we've been using, and we're going to start out with bivariant data. And what bivariant data is, it's two variables is what it includes. That's the word bi means two, and variant, just variable. And we've been using x and y hat for our variables. The x is the independent variable or my explanatory variable, and the y hat is my response variable. And the response variable is just what I'm predicting. All right? It measures the outcome of the study, what we're predicting to occur, and it's explained by my x-axis or my explanatory variable. All right, so let's look at the scatter plot here to the right and tell me, is A or B more appropriate to remove? All right, you probably said A is more appropriate to remove. Why is that? Because it's completely not in the pattern of the data. And even though this here is definitely an outlier, this would more be like, let's say this is your calories you eat and then your weight, okay? And as the calories decrease, so does your weight. And this is typically what maybe people on this diet are having. But let's say this person was way extreme and, this is not good. This is a sickly thing to do, but it's still in the pattern of the data. Okay. If you remember, we have the word leverage. And leverage is how far, if it has high leverage, how far you are away from the X bar, so from the mean, right? And so both of these have leverage in this because they're both away. My mean would be probably, my X bar would probably somewhere close to there. So both of these are definitely have leverage because it's going to, and they both are outliers. All right. This one here, though, does not change the slope. But it would increase the correlation. So B, I want you to talk about, so basically what I'm going to say is let's pretend like we don't have B at all and we don't have A at all. All right. And now we're going to add B. And what that does to the correlation now increases if I add B. All right. Now let's take B away again. And we're going to add A. And now the correlation is actually going to decrease because now instead of my best fit line being nice through there, now it's going to be much more like this. So this is taking, so you can see my slope has definitely changed, but also my correlation has changed. So my correlation would go down because now the pattern or the distance from the line is now much weaker. So when your outlier is on the line, that increases the correlation. When it's not, it decreases the correlation. So case A is the outlier, but B is what we call an influential point. So B was an influential point. Both had high leverage, but B was an influential point because it increased my correlation and it didn't change my slope. So it was within the pattern. So do the points have a positive or negative association? Well, they have a negative association because the slope is negative. So as one goes up, the other goes down. All right. Which this wouldn't make any sense. I just noticed as weight goes up, calories go down, or calories go down, weight goes up. Well, that would be a really frustrating diet. So obviously that's not correct. That would not be a correct thing. So this would be, we would have to compare something else. So as temperature goes up, let's say this is temperature, hot cocoa cells would go down. All right, so least squared regression line, LSRL. Remember what this means. It's the sum of all possible squared regression line. And remember when I did this for you here, is that if this is my line, I have a bunch of different dots. And this is my regression line. thing you can kind of build. These here are my residuals. So that's a residual. All right. Now, the key is what I'm trying to do is I'm trying to draw a line that's got these small, because I want to know what the average of these residuals are. If I add them all up, I'll almost get 0 because these are negative below and these are positive above, and I'll get almost 0. So we're going to square them so we won't get 0. And my goal is to get the smallest amount of area of all of these squares. So that's why this is called the least squared regression line. Okay, so let's look at this. If we have a set of points as has a least squared regression line of y equals 2x or 2.3x plus 17, what is the residual of the actual point? Okay, so remember RAP, residual equals actual minus predicted. This says observed minus predicted, same thing, but RAP is the way I taught you. So you're going to say what you're going to do is you say, all right, this is my X and this is my Y. And it says, what is the residual of the actual point? So that's an actual point here. So if I were to draw it, it would be basically, here's the point and here's the line. So it's not necessarily on the line. It could be above the line. It could be below the line, could be on the line, but it's not necessarily on the line. So the way you're going to do that is you're going to plug the 3 in. You're going to say, okay, this here, remember, is my predicted line. So I'm going to plug X in here. So I'm going to go 2.3 times 3 plus 17. And I get 2.3 times 3 plus 17. And that's going to be my predicted that I have here at 23.9. Now you see my residual is my actual, which is 19.5, which is here, minus my predicted, which is 23.9, which I got by plugging the 3 into the predicted equation, and my residual is negative 4.4. What that means of negative 4.4, negative 4.4 means this. So remember, look, my actual was here, about 19.5. My predicted was here. When it's a negative 4.4, that means I have my prediction was too high. All right, I'm getting all these guys out of here. All right. All right, what do a set of quantitative bivariant data look like? Make a scatter plot and look at it, and we're going to talk about how you would describe this. So if you're going to describe it, we're going to use FUDs, form, and form is easy for the AP test, so we're using FUDs, because all you have to do for form on the AP test is say linear or not linear. You don't have to describe it as exponential or logarithmic or quadratic or whatever. That's not required. Unusual features, again, gaps and outliers, same thing. D is direction. Direction is either positive or negative. And then finally, strength. Now, strength is either weak, moderate, or strong. You can use moderately strong, moderately weak. You can use anything in between there if you want. Let me just draw some examples for you. For weak, it would be something like this, where the points are not close together. Moderate, you've definitely got a pattern going, but they're kind of further apart. And then strong would be kind of more like this. They could be either in the positive or the negative direction. I could also have a strong one that looks like this. Something that's negative direction. And same thing with moderate. The direction doesn't matter. This just has to do with the strength. So the strength just has to do with the distance. The dots are from each other, really from the pattern. There are patterns that I just deleted, you saw, because they were overlaying. The formatting was weird, but you can see them on yours. Those are just some patterns that you probably would see on the AP test. You are not required to know what they are. You are just required to know that they are not linear. Okay, if a regression equation has a pattern, you're going to try to straighten the curve by using transformation. But guess what? They already straighten it for you. The AP test straightens it for you. It's your requirement to then use it from there. Let me show you an example. So if you have X and Y and it's some sort of pattern like this, and then you decide that it's going to be log X log Y. Then what you have to do, if they tell you, because then they'll do this, they'll say, oh, now it's straight. They will give you all of this, okay? So if they tell you, well, it was y hat equals 3x plus 2. So it's now they'll tell you, oh, and they'll actually give you everything, and they'll tell you, well, it's actually, no, it's not this. It's log y hat equals, let's say, 3 log x plus 2, okay? At this point, if I said, what is the predicted value for x equals 5, then I would do log y hat equals 3 log 5 plus 2. And I'd have to plug it in, and I'd have to remember that it's log y is equal to the answer. And so now you can either throw it into n solving your calculator, but if you do this, let's just gonna do this really quickly. Let's just do that one. So let's go to the calculator. 3 log 5 plus 2. Oh, and it didn't give me the exact value. Come on. It's not giving me the exact value. Okay, I have to do it from another one here, and I'll do that. Oh, that's the problem. Okay, hold on a second. Log. Okay, so that's 4.09. So yeah, so this is 4.09. So this is 4.09, but remember it's log y hat equals 4.09. So you have to remember, you have to raise that to the 10, which would be 10 raised to the 4.09, which gets you 12,302, which is way different than 4.09. And make sure you use context. Now, you can put this directly into n solving your calculator. So if you're needing help as far as solving things like this, you just put it directly into the calculator and you would n solve that first. All right. Okay, let's look at example 4. You guys ready? If the linear regression equation to find the temperature on the top of Flat Top Mountain based on Denver is y equals 1.2 x minus 34, where x is Denver's temperature and y is the temperature based on Flat Top Mountain, describe what the coefficients mean. All right, so the coefficients, I have 1.2, and I want you to describe what that means, and I want you to describe what 31 means. All right. So without looking, of course, it has the answer on here for you. But 1.2 is my slope. And so that means, remember, rise over run. So it goes up 1.2 over 1, up 1.2 over 1. And this is talking about, let's look up here. It's talking about the temperature on the mountain based on the temperature at Denver. So I'm going to say this is going to be temperature in Denver and temperature in the mountain, because that's what I'm predicting. That's what gets predicted. So I'll put a hat over there just so you see that I'm predicting the temperature on the mountain. So that's why it says 1.2 means for every degree the temperature goes up in Denver. Yep, goes. It's because this goes up to the right in Denver. It rises 1.2 on top of the mountain, and that's how you would have to describe it. And negative 31 means when the temperature in Denver is 0, because this is my y-intercept. The temperature on Flat Top Mountain is 31 degrees below, or negative 31. All right, and what does r equals 0.87 mean? Well, that's positive, and anything we try to say, let's say anything between R between 0 and 0.3 usually we call weak, either positive or negatives, by the way. I say about between 3 and 0.7 or 0.65 or something like that, we call moderate. And then anything above 0.7, I know I'm kind of I'll just make these inclusive for you. R to 1, we call that strong. And of course, anything in between there is moderately strong, moderately weak, things like that. So that's why we have this here as a strong. There's positive linear correlation between the two temperatures. And I'm going to add strong because that is how we're FUDs again. Now for this is how we describe R. R is described, you can't have an unusual feature in a correlation coefficient, so that's why you don't have to have the U, but that's how you describe R. Strong positive linear correlation between the two temperatures. Okay, R squared, if you remember, R squared is the percent of total variation in the temperature on Flat Top Mountain associated with the variation in the temperature in Denver. So this is the temperature of Flat Top Mountain is always my Y associated with X. So I have the percent of my, is a percent of what I have of my total variation or percent of accounted for, my errors accounted for. So of the variation of my Y is accounted for on the least squared regression line by X. So that's kind of the template that you would use for that. Okay, when you make predictions on the regression equation, it might not be useful outside the range of data, which is called extrapolation. Remember extrapolation. So for this particular one, we don't have it on here. But if I had on this particular problem, if I just had this here and I was going, let's say from it was going to negative 31, so we can even go maybe from negative 40 and maybe went to 20 degrees, something like that. I don't know. And this was negative 30 to 60, whatever. But if I predicted anything outside my range of data, if this was all my range was, then I would not be positive that it would continue to hold that same linear pattern. And that is called extrapolation. So be very careful and make sure that you stay within your range. I'm sorry, domain. Okay, just because two things are associated doesn't mean one causes the other. We have talked about that in so many different ways. There may be different lurking variables or one that has an effect on both. This is called confounding. Remember, we have confounding if something is causing this, and this confounding, actually the way I drew it for you with these letters, I should use the same letters for you so it won't get confusing. I had A causes B, or is there a C confounding? Not sure, and that's confounding. And of course, to do an experiment, what do we need? A well-designed, controlled experiment. What's well-designed? Control, randomization, replication. And that's what we need to know so that we can reduce confounding variables, and we never can eliminate things, but we can reduce them, and that we can have causation. Okay, categorical data, a categorical bivariant or multivariate data. Okay, so you're going to make a table and figure out your totals. Percentages of rows and totals could be useful, and chi-squared could be useful. So this is just saying, all right, is this categorical or quantitative data, and how do I use it? Well, it's just telling you to go ahead and organize your data, and when you organize your data, then it becomes pretty obvious of what type of test you need to do. All right. Okay, so I'd like you guys to take 12 minutes, or excuse me, not even 12 minutes. I don't think you need that. I think, about 10 minutes probably? 10 minutes to do this problem. So you're going to put me on pause here for a second. Yes, put me on pause. And you're going to do this for 10 minutes, and then we'll go ahead and look at some of the multiple choices and see what you have to do. So put me on pause and go ahead and try this and see how you do. And I will help you in a second. Okay. If you didn't put me on pause, put me on pause. Hopefully you did. Since the Hill Valley High School eliminated the use of bells between classes, teachers have noticed that more students seem to be arriving into a class a few minutes late. One teacher decided to collect to determine whether the students and teachers and watches displaying at the correct time at exactly noon. The teacher asked 9 randomly selected students and 9 randomly selected teachers to record the times of their watches at nearly half a minute. The ordered data showing minutes after 12 as a positive value and 12 as a negative values are shown below. Okay? Construct parallel box plots after doing these. So what you guys should do to be able to do these is I'm going to put students here and teachers here. And I'm going to put the scale down here. And this was going to be my minutes. And I'm going to remind you guys of how to do box plots. So if you can't remember how to do box plots, let's go ahead. Everybody get your calculator out. Okay, everybody needs to get their calculator out, please, right now. Get your calculator out. If you haven't, please get your calculator out. All right, so we're going to go ahead and go to a spreadsheet. Let's add a new one. And I'll call this one students. Okay. And we'll call this one doesn't want to go. Okay, I don't know what's going on here. Let's try it again. All right, so we'll call this student here, and let's put the data in for this one. And this is negative 4.5, negative 3, negative 0.5, 0, 0, 0.5, 0.5, 1.5, and 5. And then teachers, negative 2, negative 1.5, negative 1, negative 1, negative 0.5, 0, 0, and 0.5. Oh, missed something. Oh, I have 2 negative 1.5, so I need to put, oops. Okay, order doesn't matter because they're not paired together, so it's okay. So let's go ahead and go to menu, and add data statistics, and I'm going to do my student, and we're going to go to menu, plot type, box plot. And there's my box plot. And I can also add another one. And you can do them together too. So student, teacher, and then I have menu type box plot. Okay, so we're going to go ahead and make sure we have the same scale. So this goes from negative 2 to 0.6, and my other one runs from negative 5 to positive 5. So I'm going to have to go that, so it's going to have to have the same, negative 5, and so that's the Student was from -5 to 5. And so we're going to be looking at these couple things. You can see we need Q1 at 1.75, minimum at 4.5, my median at 0, my Q3 at 1, and my maximum at 5. So I need all of these, -4.5, 1.75, 0, 1, and 5. So I'm going to put it here. Zero, -1.75, so here, and then 1, and then 5. And you need to max 5, Q3, 1, median, 0, Q1, 1.75, and minimum was -5. All right, we're going to do the other one. Which this one runs from -2, and then it has a Q1 at -1.5, median -1, Q3 at 0, and 0.5. So we're at -2, -1.5, and -1. -2, -1.5, and -1 so far was this. And I have at 0 and at 0.5. So 0 and at 0.5. So obviously much different. So this is at Q1 was -2, minimum was at -2, Q1 was at -1.5, median was at -1, Q3 was at 0, and max was at 0.5. So you can see the distributions compared to each other. It says based on the box plots in part A, which of the two groups, students or teachers, tend to watch the times that are closer to the true time. Well, obviously, we would say the teachers have less variability than students. And they're and closer to 0 as well, with a max of 0.5 versus 5 for the students, and a range, or I guess a min, I wanted to put a min first, of -2 versus -5 for the students, and a range of, we have 0.5 too, so of 2.5 for teacher, and 10 for the students. So what I tried to show here with detail and context and data was that the box plots for the teacher was closer. The reason 0 is because that's going to be closer to the actual time since they subtracted it. So the teacher wants to know whether the individual students' watches tend to be set correctly. She proposes to test HO is mu equals 0 and HA is mu is not equal to 0, where mu represents the mean amount by which all students differ from the correct time. Is this an appropriate pair of hypotheses to test to answer the teacher's question? So it says the teacher wants to know whether the individual students' watches tend to be set correctly. So if it's set correctly, it's not asking if it's greater than or less than. It is asking if it's not equal to. And so, yes, I would say that, yes, it is appropriate, because HO, mu equals 0, would represent that, that would mean that the watches are correct. Means that the mean is 0, means there's no difference. And then mean is not equal to 0 would represent that the watches are not correct. And so obviously if I got a low p-value. So if p-value was less than alpha, then that would lead me to believe that the watches are not correct. Okay. All right. I gave you guys the answers on this. I'll go ahead and have you guys finish. If you should have done, I know some classes I said 10 and some classes I said 12, but you should have gone up to a 10 or 12. And then what I'd like you to do is finish these. You've got 30 total. So if you don't finish them in class today, I'm going to have you finish them for homework this weekend, and I'll have you upload them. They've got 28, so not too bad. So as long as I get, let's say 20 uploaded by the end of class, and the rest of them can be uploaded by this weekend. So this can be like Sunday night, 12 a.m., like midnight. All right, I will give you guys the data, and also be looking for a video on this so you guys can understand how to do this. Make sure that when you do this, you must show work. Now, sometimes you don't have work to show, so just give me a short explanation. Okay, so then, because I'm going to be giving you the answers, so then that can show me that you understand how to do this. All right, thank you very much, and I will see you guys virtually tomorrow.